Imagine stepping out onto this, super bustling city street. In just a fraction of a second, your visual cortex just effortlessly segments all the chaos.
Right, you don't even have to think about it.
Exactly. You identify the yellow chassis of a taxi, you track where a cyclist is going, and you even notice a pedestrian who's like partially hidden by a street lamp.
Yeah, your brain processes the scale, the depth, occlusion, all of it without breaking a sweat.
But if you feed that exact same visual data to a computer camera, it registers absolutely nothing but a flat, meaningless matrix of red, green, and blue pixel intensities.
Right, it's entirely blind to the context. I mean, a machine doesn't see a car. It just sees a cluster of pixels where the numerical color values suddenly shift.
And converting that matrix of numbers into actual semantic understanding is, well, it's the core challenge we're tackling today. So welcome to this deep dive.
Glad to be here.
Today, we are unpacking the mechanics of object detection, and we're drawing from a really comprehensive foundation of computer vision research.
It's a fascinating area.
It really is. Our mission for you today is to explore exactly how machines are engineered to localize and classify objects in digital space.
We'll be looking at the mathematical features they search for and the big leap from those old, exhaustive sliding window searches to modern global neural networks.
Yeah, and we'll even get into the super sophisticated ways developers are bridging the gap between simulated training environments and the chaotic, unpredictable real world.
Which is huge, right?
Right.
Because whether you're looking at broadcast algorithms perfectly tracking a football's velocity in real time,
Oh yeah, I love seeing that during games.
or the vision systems that let an autonomous vehicle tell the difference between a shadow and a pothole at 60 miles per hour, this is the exact architecture making it happen.
It really is the magic behind so much of our modern digital infrastructure. So let's just dive right in.
Sounds good.
To understand how a machine detects an object, we first have to look at how it actually defines one.
Yeah.
Our sources point out that, well, before the whole era of deep learning, machines relied really heavily on human-engineered features.
Right, humans had to manually tell the computer what to look for.
Exactly. It reminds me of this highly mathematical game of I Spy. Like the computer isn't looking for the big picture concept of a square.
No, it has no concept of a square.
Right. It's scanning the pixel matrix for abrupt changes in contrast that mean there's a vertical edge, and then it combines those with horizontal edges and calculates if the intersecting angles are perfectly perpendicular.
It's literally just geometry masquerading as vision.
Yeah, it's wild to think about.
And that process relies on identifying specific measurable metrics that stay consistent, regardless of the lighting or how zoomed in the image is.
Give me an example, like how would that work for something complex?
Well, take face identification. The system executes a search for structural relationships. It measures the gradient of pixel intensities to find the edges of the eyes, the bridge of the nose, the lips,
So it's just looking for contrast lines on a face.
basically. And then it calculates the spatial ratios. Like it literally measures the exact distance between the pupils relative to the width of the mouth.
Oh, wow.
Yeah. And if those mathematical ratios fall within a specific statistical threshold, the algorithm just flags it as a high probability of a face.
Okay, but calculating those pixel gradients sounds computationally agonizing if you are doing it blindly.
Oh, it was.
Like if I have a massive 4K image and I'm looking for a pedestrian, historically I'd have to use what they call a sliding window approach, right?
It's the sliding window.
Where I'm essentially taking a tiny digital magnifying glass, checking the top left corner, shifting it a few pixels, checking again, scanning the entire image.
And then doing it all over again with a slightly larger magnifying glass, just in case the pedestrian is closer to the camera.
That just sounds so inefficient. The computational overhead for that exhaustive search must be just massive.
It's huge. You're running a classifier on thousands of overlapping crops of the exact same image.
Which is why things had to change.
Exactly. That bottleneck is what drove the whole paradigm shift toward modern neural network architectures. Specifically, models that can process the image end-to-end.
Right, and the text highlights YOLO as a major breakthrough here, which stands for You Only Look Once.
So it's a great name for an algorithm.
It really is.
Yeah.
So instead of sliding a window around thousands of times, YOLO just feeds the entire image through the neural network in a single pass.
Yep, one look.
It overlays this grid onto the image. And each individual cell in that grid is responsible for predicting the presence of a bounding box and the probability of a specific class.
Like predicting if it's a pedestrian or a car simultaneously.
Right. And by analyzing the image globally like that, the network actually leverages the context of the entire scene.
Which is a game changer. Because a grid cell doesn't just look at the pixels inside its own little boundary.
Right. The convolutional layers allow it to understand its relation to the surrounding architecture.
Exactly. It makes the detection infinitely faster, which is, the absolute prerequisite for anything requiring real-time video processing.
You can't have a self-driving car pausing to run thousands of sliding windows.
Exactly. You'd crash before it finished processing one frame.
Right. But, okay, the speed is incredible, but the way these neural networks build their internal logic during training introduces some really fascinating vulnerability.
Oh, definitely. The black box problem.
Yeah. The source material outlines this classic problem using starfish and sea urchins.
I love this example.
So good. So let's say we feed our network thousands of training images. Over time, the distributed nodes in the network learn that a starfish is highly correlated with two things: a star-shaped outline and a ringed texture.
Okay.
And conversely, it learns a sea urchin correlates with an oval shape and a striped texture.
Right, so the network is continually adjusting its internal weights to minimize prediction errors. It builds the statistical map of the features that define those two specific classes.
But the real world is full of anomalies, right? So during training, what happens if the network processes an image of a rare sea urchin that just happens to have a ringed texture instead of a striped one?
Well, the network has to reconcile that anomaly somehow.
Right.
So it establishes what we call a weakly weighted association between the intermediate nodes representing that ringed texture and the final output for the sea urchin class.
Okay, so that weak association is essentially the network just noting an edge case.
Exactly. It doesn't heavily prioritize it, but the pathway exists in the math.
Okay, so fast forward to the testing phase. We feed the network a novel image of a beach. In the center is a totally normal starfish with its typical ringed textures.
Normal starfish. Got it.
But sitting next to it is just a random oval rock, a shape the network hasn't explicitly trained on.
Oh, I see where this is going.
Right. So my understanding is that the network sees the oval rock, which lightly triggers the geometry nodes for a sea urchin because of the oval shape.
Yeah.
And simultaneously, the ringed texture of the nearby starfish triggers that weakly weighted anomaly pathway we just talked about.
Exactly. And the combination of those two independent, weak signals,
The oval rock and the ringed starfish.
yeah, they aggregate within the hidden layers of the network. The combined mathematical weight surpasses the activation threshold, and boom, it results in a false positive.
Wow.
The system will just confidently output a bounding box for a sea urchin over a completely random rock.
It's basically a hallucination born of statistical probability. Like, the features aren't isolated, they are entangled across this complex web of nodes.
And that entanglement is exactly why evaluating these models requires absolute mathematical rigidity.
We can't just casually observe that the AI is, like, mostly right.
No, not at all. We have to benchmark it against a strict ground truth.
Okay, let's talk about that. When we talk about ground truth bounding boxes, my mind immediately goes to the problem of occlusion, or fuzzy borders.
Yeah, annotation is tough.
Like, if a human annotator is drawing a box around a crafting sign for the training data, that's pretty straightforward.
Sure.
But what if they are annotating a pedestrian standing behind a parked car? The annotator has to decide whether to draw the box only around the visible torso, or do they estimate the geometry of the entire hidden body?
Right, that digital chalk outline becomes highly subjective.
Exactly. So if the human draws this subjective box, and then the AI draws its own box, but it only covers half of the human's box.
Does it pass or fail?
Yeah, who decides that?
Well, to remove that subjectivity during the evaluation phase, developers use a similarity measure called intersection over union, or IOU.
Intersection over union, okay.
It compares the ground truth box drawn by the human against the predicted box drawn by the algorithm.
And the math on that is actually really elegant. Like, you calculate the area where the human's box and the AI's box perfectly overlap.
That's the intersection.
Right, and then you calculate the total area covered by both boxes combined, which is the union. You divide the intersection by the union, and you get a strict percentage of similarity.
Exactly. So a score of 1.0 means perfect pixel alignment, and a score of 0 means the boxes don't touch at all.
Okay, makes sense.
In practice, evaluating a model requires setting an IOU threshold. It's frequently around 0.5.
So 50% overlap.
Right. If the algorithm predicts the correct class and the bounding box overlaps the ground truth with a score higher than 0.5, it registers as a true positive.
Okay, but if the AI's box is too sloppy, say it only captures the top corner of the traffic sign and it scores like a .3.
Then it's penalized as a false positive, even if it correctly guessed it was a traffic sign.
Wait, really? Even if it knew what the object was?
Yeah, because it failed the localization test. Knowing what it is isn't enough if you don't know exactly where it is.
Okay, wow. And if it misses the sign entirely, generating no box at all, then the ground truth registers a false negative.
You got it. The system also has to account for duplicate predictions, by the way.
What do you mean?
Like if the algorithm draws 3 overlapping boxes around a single traffic sign.
Oh, because it's just super confident.
Yeah, but only the prediction with the highest score above the threshold is awarded the true positive. The other redundant boxes are heavily penalized as false positives.
To train the model out of making cluttered, uncertain predictions.
Exactly. Which brings us to MAP, or mean average precision.
Right. Because grading a model isn't just about a single image.
No, it's about evaluating the trade-off between precision and recall across thousands of images and dozens of classes.
So the MAP aggregates how well the model avoids false positives while simultaneously actually finding all the real objects in the dataset.
It is a very unforgiving report card.
But I mean, it needs to be unforgiving, right?
Absolutely. Because a model might achieve a stellar MAP score in a controlled laboratory dataset, but deploying it into the real world introduces what we call the domain gap.
The domain gap. This is fascinating because it exposes just how fragile these statistical models can be.
Oh, they're incredibly brittle.
Like, you can train an autonomous vehicle's vision system on millions of high-resolution, perfectly exposed photographs of city streets.
Beautiful sunny days in California.
Exactly. But the moment you deploy that vehicle into a torrential downpour at midnight in, like, Seattle...
The data distribution of the camera feed completely diverges from the training data.
Right. The geometry of a car is exactly the same, but the lens flare, the water droplets, the noise profile, it's all entirely alien to the neural network.
And as a result, the algorithm's confidence scores just plummet.
So to bridge that gap, you need training data that perfectly mimics the target domain, but manually annotating millions of frames of nighttime driving footage.
It's in the rain.
Right, with pixel-perfect bounding boxes. That is economically and logistically totally unfeasible.
Which leads to literally one of the most brilliant hacks in modern computer vision.
Yes. I loved this part of the source material. To bypass the massive manual labor of human annotation, developers are actually training real-world autonomous systems using video game engines.
It's genius.
It is, because in a rendered simulation, like a Grand Theft Auto-style engine, the computer already knows the exact spatial coordinates of every single digital pedestrian, stop sign, and vehicle.
Right, because it generated them. So the engine can automatically pump out millions of flawless ground truth bounding boxes per second.
For free.
For free. The simulation provides infinite, perfectly annotated geometric and physical interactions. The vehicle can learn how a digital pedestrian steps off a curb or how cars queue at a traffic light.
But the rendering, I mean, no matter how advanced it is, it still possesses synthetic textures and lighting, right?
Yeah, it still suffers from a domain gap when compared to a real gritty dashboard camera.
So I imagine that's where generative adversarial networks come into play.
GANs, exactly. The source material mentions using unsupervised domain adaptation, specifically image-to-image translation like CycleGAN, to fix that visual disparity.
So my understanding of a GAN is that we are basically pitting two separate neural networks against each other to force an evolution in image quality.
That's a great way to put it. You have a generator network and a discriminator network.
Okay.
The generator's job is to ingest a frame from the video game simulation and alter its pixel values to make it look like actual dashcam footage.
So it adds like realistic asphalt textures or simulated lens distortion.
Yeah, and accurate shadow diffusion, real-world grime.
And then the discriminator acts as the counterfeit inspector.
Exactly. It looks at the generator's altered image alongside actual unannotated footage from the real world and tries to guess which one is the fake.
Wow. And the two networks just train simultaneously.
Right. The generator constantly refines its image translation to trick the discriminator, and the discriminator constantly sharpens its ability to spot synthetic artifacts.
And through these CycleGAN architectures, this translation happens while strictly preserving the underlying geometry of the original simulation.
Right. The stop sign doesn't change shape or location. It stays exactly where the free bounding box is.
But its texture and lighting become completely indistinguishable from reality.
The end result is a data set of millions of photorealistic driving scenarios, complete with perfectly accurate bounding boxes.
The AI learns the physics from the game, but it trains its visual sensors on the gritty, translated reality generated by the GAN.
It is a remarkable synthesis of simulated data and real-world adaptation.
So let's pull all of these threads together for you listening. We started by breaking down how a machine identifies edges and pixel gradients to find mathematical geometry in a flat image.
We explored how architectures like YOLO revolutionized the field by evaluating the entire image grid in a single pass, completely moving away from sliding windows.
Right, and we examined the internal weights of intermediate nodes and how intersecting weak signals, like our rock and starfish, can trigger those crazy false positives.
We broke down the rigorous evaluation metrics, right? Intersection over union and mean average precision, the tools that force these models to actually be accurate.
Finally, we looked at how the industry bridges the domain gap, employing adversarial networks to translate synthetic video game environments into hyper-realistic training data for autonomous systems.
The sheer layers of abstraction required to teach a computer to just see are staggering.
They really are, and the practical application of this is everywhere.
Oh, absolutely. I mean, the next time you see a sports broadcast, overlaying graphics perfectly onto players in motion.
Or your phone's camera instantly locking focus onto multiple faces in a crowded room.
Exactly. You are witnessing the real-time execution of convolutional layers, grid predictions, and IOU calculations.
It's this invisible framework layering semantic meaning over a totally chaotic world. But, digging into the precise math of how these networks weight their visual features leaves a lingering thought about vulnerability.
Vulnerability in what way?
Well, we spend so much time bridging the domain gap with hyper-realistic simulations, right? Assuming that if the training data looks real enough, the AI will perform flawlessly.
The assumption being that the model's statistical representation of, say, a stop sign is robust.
Right. But it's exactly the opposite, actually, because we know the model isn't seeing a stop sign. It's seeing a highly specific matrix of gradients and pixel associations.
Which opens the door to adversarial attacks.
Exactly. Researchers have demonstrated that by placing a few carefully designed, seemingly random geometric stickers onto a physical stop sign, you can completely subvert the neural network.
Right. To a human driver, it's clearly just a stop sign with a few stickers on it.
But to the AI, those specific pixel disruptions trigger a cascade of weak signals that confidently misclassify it as a 45-mile-per-hour speed limit sign.
A targeted disruption of the hidden layers.
A physical exploit of the algorithm's mathematical blind spots. It's a really sobering reminder that no matter how sophisticated the neural network is or how flawless the simulated training data might be, machines and humans are fundamentally perceiving two entirely different realities.
Very well said.
Definitely something to ponder the next time you trust a vision system to navigate a busy city street. Thank you so much for joining us on this deep dive. We will catch you on the next one.